Hello everyone, welcome back to the another session in design and analysis of algorithms. Today we'll be going to talk about optimal binary search tree. So this topic you'll find in third unit as topic number 9. So this video will be going to cover what is binary search tree and what is optimal binary search tree, and we are very much aware that every searching operation will be having successful case, unsuccessful case. What do you mean by successful case? The element what I would like to search in the tree is found. So when the element is founded, then it is successful. If you did not find any element what you are looking for, then it is unsuccessful search. So we'll be going to know successful search comparisons, unsuccessful search comparisons, and we'll take an example. Then we will calculate the cost of the binary search tree. Then we'll look at how dynamic programming can be applied on optimal binary search tree. We'll solve a problem by taking some example from previous question paper. So I'm sure that I cannot cover all these content in single video, but we'll do one thing. We'll make up to this into one video and this into the other video. Whoever is watching this video, I suggest to watch the next video also for the better understanding of this topic. Now let's get started. So what is binary search tree? Now a binary tree is a tree where it will have at most 2 children. That is called as binary tree. Now that means if I construct any tree, if I considered any tree, now can I call this as a binary tree? Yes, it is a binary tree. Can I call this as a binary tree? Yes, it is a binary tree. Can I call this as a binary tree? No. Why? The reason? Because it is having 3 children. So I told you that binary tree will be having at most 2 children, not more than that. It can be called as a tree, but it cannot be called as a binary tree. So the point is what? Binary tree always will have at most 2 children, either 0 or 1 or 2. Now what is binary search tree? Binary search tree, I am calling these elements with the name of keys. Now what is binary search tree? The binary search tree, the keys are arranged such that for any node, if you take, all the smaller keys are on the left hand side. All the larger keys are right hand side. Now, when you given with some set of elements, what we will be doing is, we will be making one element as root element. So this is my root element. If I pick the other element from the list of elements, I'll be going to compare the second element with the root element. If I found that is lesser, then I will be putting that element under left subtree. If the element what I'm going to pick from the list is seems to be greater from root element, then I'll keep that element in the right hand side, because it gives an advantage for searching. And this is called as binary search tree. Okay, now I want to search. Let's assume that I wanted to search 30. How to search 30 element from this tree? Start from the root. So root element is what? 40. Root element is 40. That means root double is equal to 30. Now root is what? 40. 40 double equal to 30. It is not true. Then we'll write the other condition. The other condition is what? Key element, whatsoever element I wanted to search, whether it is lesser from root. If it is less than from root, my searching operation, binary search operation, will be at left hand side. If it is not, that means if key is not less than from root, we'll write other condition, and now binary searching operation will be right hand side. Now let's take this example and understand. So 30 is my key element what I wanted to search. So root double equal to 30, element is not match with this. So obviously condition fail and we'll come down to the other condition to check. Key less than root. Now 40 and 30, 30 and 40. 30 is lesser from 40. So you will be having a probability that the element will be at left hand side. Now we'll start searching left hand side. Come. So left hand side, left subtree is there. Now 30 will get compared with the root element of left subtree. Now it is what? Greater than from this root. That means element may have at right hand side of this 20. So we'll come down. Now it will becomes a root node, right? Maybe you cannot see any children here, but as far as the tree is considered, it is also root when you come down to here. Now again 30 double equal to 20, 30 double equal to 30. Match found, then element is found. For searching 30, how many comparisons we have done? How many comparisons? We compared with this element, 1 comparison, and we also compare with this element, 2 comparisons, and finally when you come down from 20 to 30, again you compare over here, right? So how many comparisons? The maximum comparisons for any element is equal to the level of it. So in the case of 30, how many comparisons we made? 3 comparisons. Now, let us take the other example. Now I wanted to search this 50. Now, for this time, my second case is 50 is my searching element. Then, how many comparisons it also required? We'll be going to compare with the root element. Now this time not 30, it is 50. Compare with the root element. Match not found. So we'll go to the other condition. 50 less than 40. 50 is greater, so it is also not true. We'll come here. Key greater than root. Yes, it is true. Now it will get, we'll be going to print the search is found. So how many comparisons for this time? 1 and 2 and 3. So for this 50 also maximum number of comparisons are 3. If you take any element, the maximum number of comparisons are 3. Now let's suppose I wanted to search this 40 only. How many number of comparisons? 1. For 20, how many number of comparisons? We will start with this root node. If it is not, then we'll come to the second condition. Now this time it will be matched. So how many comparisons it is required? 2. For 10 it is 3. For 30 also 3. For 60 it is 2. For 50 it is 3. For 70 it is 3. So what I am trying to say is the maximum number of comparisons are exactly equal to the level of the tree. The level of the tree. Now what is this level of the tree? Level of the tree is, this is what the first level, and this is what the second level, and this is what the third level. So maximum number of comparisons always will be equals to level of the tree. Now it is what successful case. In both the cases, in 30 case and in 50 case, we found element in the tree. That means it is successful search. Now let's see unsuccessful search. That means I wanted to find out the element which is 9. So 9 actually is not presented in the tree, but I would like to search 9. Then how my searching operation will be done? So I'm just comparing with the 40. I found 9 is less than from 40. So as far as the condition is considered, my element will be at left hand side, will come at left hand side. Now again 20 is found greater and 9 found it is lesser. Then we will search at left hand side of this 20. Now we'll come to this 10. Now here 10 seems to be greater than from 9. Then 9 probability will be here. Correct? So why it will be here? 9 is lesser than of 10. 9 is actually not presented. If it is presented, it would be under 10. So this is what? Minus infinity to 9. The probability 10 after the 10, if you wanted to take any element, that will be probably from minus infinity to 9. Now, in the same case, now I am taking this. Right hand side of 10 will be what? Any guess? It is 10. Now, obviously, 10 right hand side should be greater than of 10. So, that means 11 to 19. Because 20 already the root of that subtree. Right? So, now, I am just drawing this square boxes. Circle boxes are to represent the keys what are available in the list. Square nodes or square symbols I am representing for unsuccessful elements, the element which is not founded, but there will be a probability. If it is in the case that you wanted to take unsuccessful search case, the probability in the tree is I am calculating. So 9 is not found because I have reached till the end of a binary search tree, and key element is not found. So if a element is not found, then the search is called as unsuccessful search. So we need to know the amount of comparisons that we are doing, and that amount of comparison is nothing but the cost of searching in a binary search tree. Now, more thing, unsuccessful nodes are representing with dummy nodes. I told you this dummy nodes. Square boxes are representing dummy nodes, and these nodes are what? Unsuccessful nodes. Now, so I am taking unsuccessful nodes, these. So total how many elements you have? 1, 2, 3, 4, 5, 6, 7. Total 7 elements, right? Your n value for this tree, is 7. N is equal to 7. And that means what? Keys availability. I'll just make it is fresh to understand. The total number of nodes, which are n is equal to 7. Correct? That means successful nodes. Successful nodes in this binary tree is equal to 7. Now what about unsuccessful nodes? That means square nodes. Square nodes of a tree is equal to n plus 1. You can draw here. 10 can have 2 dummy nodes. 30 can have 2 dummy nodes. 50 can have 2 dummy nodes. 70 can have 2 dummy nodes. So calculated, it will be n plus 1. So total it is 8. Now, from this what we have to understand is successful search, unsuccessful search, successful number of comparisons, unsuccessful number of comparisons, always it will be n plus 1. 10 you found over here. If you have any element in the next level, that will be here, right? So basically the probability of successful nodes will get started with the 1. And for unsuccessful, we'll start with the 0. Right? Now we'll take an example and we'll just move to understand how many comparisons we'll take, the maximum number of comparisons. That gives the cost of the tree. The reason why I'm calculating maximum number of comparison is that is what cost of the tree. So now we'll take some example to understand in better way. Let us assume that you have 3 keys, 10, 20, 30 or 3 keys. For same set of keys, there can be many possible binary trees. And we'll see few among it. Now 30, 20, 10. This is one binary tree. The other one 30, 10, 20. This is one more binary tree. 20, 10, 30. This is the other one. 10, 30, 20. and this is the one more, 10, 20, 30, right? So how many trees we do have? 5 trees. How to calculate the possible binary trees from the given keys? The formula is T of n is equal to 2NCN by n plus 1. Now T of n is equal to 2 into n value is 3. 3C3 by 3 plus 1. 2 into 3 is 6C3 by 4. Now 6 into 5 into 4 by the formula I am writing, NCR formula I am writing. Six into 5 into 4 by 3 factorial, 1 by 4. This 4 I am writing. Now 4, 3 factorial is 3 into 2 into 1. 3 into 2 is 6. 6 will get cancelled and total is 5. This 5 is what? Maximum number of comparisons. So for the moment when you considered some elements or keys to construct possible number of binary trees, you can simply apply this formula. Then you will be coming to know how many possible binary trees will come from the given keys. So as far as this example is considered, possible binary trees are what? 5. So now I am considering the 5 to move. Now what you have to calculate? The maximum number of comparisons. Now we considered a binary search tree which gives a less number of comparisons. Now, so once check the maximum number of comparisons to search any of the element. So to search this 30, it is 1. To search this 20, it is 2 comparisons. To search this 10, we need 3 comparisons. In the before slides only, we were come to know that one relation, the maximum number of comparisons always will be equals to level of that tree. Now level of the tree is what? 1, 2, 3. So it is also required 3 comparisons, maximum comparisons. Now the level of this tree is what? 1, 2. So we need only 2 maximum comparisons, and 10, 30, 20. It is also 3 maximum. It is also 3 comparisons. Now, so we were drawn some binary trees and we got all 3 maximum comparisons except of this tree. So it is complete binary tree, right? For complete balanced binary tree, you got maximum number of comparisons or 2. So as of binary search trees belongs to a minimization problem, we'll take the less number of comparisons to solve the problem. We'll take only this tree. We'll not take all the trees because it is an optimization problem. We'll take whichever tree will gives you the low number of maximum comparisons, the tree. Then that tree will be going to considered in order to calculate the weight of the tree, the cost of the tree, and this. So we'll take the other example to see. So now this time I am taking the example with the 4 keys. 10, 20, 30, 40. These are what? 4 keys. Now, what are the maximum number of possible binary trees? Just now I told you the formula, right? 2NCN by n plus 1. That is, n is equal to be given with 4 keys. So now the possible number of binary trees are is equal to 8C4, right? 4 plus 1 is 5. I am just writing this formula. 8 into 7 into 6 into 5 and 4 factorial. I am just writing 4, 3, 2, 1. So this formula you already know from the mathematics, right? This NCR is equal to NC n minus 1. N minus R. That means NCR is equal to n factorial by R factorial into n minus R factorial. I'm just applying this formula. That's it. Right. Now 5, 5 and 3 to 6, 6. and 4 2s are 8. Totally 2 into 7, which is 14. That means 14 binary trees are going to considered for this problem. Now my question is, as the way you are increasing the number of keys, it is also quite natural, quite true that you will get more number of binary trees, and we cannot calculate all the trees and the cost of it, maximum number of comparisons. In the previous example and this example, previous example we have only 3 keys, but we got 5 binary trees. So drawing 5 binary trees is not a big task. But the moment when you are increasing the total number of keys, proportional to it, the number of possible binary trees also will get increased. Now here comes, we will take only few trees to calculate successful, unsuccessful. Once you know how to move forward, then you will be understanding which binary tree we can consider. So if I consider only one binary tree from this 14, maybe that 13 will have low cost, and that is the reason why we'll calculate cost of the binary tree, and we'll see that example how to we cannot take all 14, but we will take 14 binary trees in indirect way. We cannot draw it, will not draw also, will not take a big problem, will not take a big risk, but we'll be going to consider all this 14, because our aim is what? You have to reduce the cost of it. You have to consider the low cost which gives from binary tree. For that we'll take some formalized methodology, but as of now we'll work on this n equal to 4 to calculate successful and unsuccessful search, and what is the probability of successful search and the unsuccessful search, and we'll calculate even the cost of the tree. So it is, in the previous example we just calculated the number of comparisons and the level of the tree, but this example I want you to learn bit more, that is how to calculate cost of a binary search tree. So optimal is what? Now this time I am talking about optimal binary search tree. What do you mean by optimal binary search tree? A problem of optimal binary search tree is that if the key is given and probability is given, we have to generate a binary search tree such that the cost is minimum. So this is what optimal binary search tree. So just optimal word will come before of binary search tree. Optimal means correct solution. That means we have a constraint that it should be a minimum. So cost should be minimum. Then the binary search tree is called as optimal binary search tree. Now we'll proceed with this example. We'll take this example. Now my example 2. Now you given with some 4 keys. Now you asked to compute the cost of the tree. Okay. Now we'll proceed with the solution. How to calculate that, the same. So in the previous slide, we come to know possible binary trees for this example is 14. Okay. Now if there are n nodes, there will be n plus 1 square nodes. That also we were discussed, right? N nodes, then n plus 1 square nodes. What is your n value? 4. So that means you will be having only 4 nodes. So what is n plus 1 square nodes? That unsuccessful nodes will be 5. Now let's draw it. Now I am just drawing here 20, 10, 30 and 40. So I am not going to take 14, but I will take few of it. 30, 20, 40, 10 and 40, 20, 10 and 30. Now you just draw the unsuccessful nodes, that means square nodes. So square nodes should be 5 according to the formula. Now make sure that you got 5 or not. You also draw with me so that in examination you feel more comfortable to proceed with the solution. So what these square nodes are called as, these are dummy nodes, because searching the unsuccessful key element is maybe possible, right? We will be asking the programmer to search the element which is not in the list. So once you done all the searching operation, then only you can conclude that search is failed or it is an unsuccessful search. So there are chances of having a successful search and unsuccessful search too. Now we'll take some probabilities of the same. So Pi is the successful probability, Qi is unsuccessful probability. I'm just writing some probabilities, 0.1, 0.2 and 0.1, 0.2. So when you add all this, it should give the one answer. So I'm taking in that way, 0.15 and 0.5, 0.5. Now you may ask a question that why the reason you have taken P successful probability is 4 and unsuccessful probability is 5. So it is respective to the nodes. My probability Pi indicates probability for successful nodes. How many successful nodes you have? 4. Q represents that unsuccessful probability. How many nodes you have? 5. So it is respective to the number of nodes what are available. Now, so here what the thing we'll be going to do next is, we'll be going to calculate the cost of searching. Cost of searching a element from this tree, that I'm going to calculate. So now how can I calculate? There is a formula to calculate the same. Now let's take this tree and we'll calculate. The first tree I'm considering 30 and it is dummy nodes I'm taking 40. Now indicate the probabilities also. In the previous slide I mentioned the probabilities, 0.1 and dummy node also having the probability. Now so this is what we are going to calculate, the probability, the cost of this total tree. So tree consists of nodes, tree consists of square nodes, tree consists of circle nodes, tree consists of square nodes. So put together you'll get the cost of the tree. So the cost of searching 20 is what? It is in level 1. Cost of searching 20 is what? So 1 into what this 1 in, I'll write here 1 into what this 1 indicates, level. 20 is at level 1, 10 is at level 2. Now come to this one, very important, come to this dummy node. This dummy node is at which level? It is at third level, but I'm not coming to third level as element is not there. I'm at second level itself, but for appearance you can find it is in third level. As you don't have any element, will not come to this, but our expectation is what element can be here. So we will take, if you consider it is 3, then we will take it is level -1. Did you understand? Now the same. Now I am just moving to calculate the cost of the entire tree. 1 into 1 indicates level and 0.2. 0.2 indicates probability of that node to search. It is it is 20 element cost. Now the next is what? 2. Level 2 is what? 10 element. Now I am writing that element. 2 into what is 2 indicates? Level into 0.1. 0.1 indicates probability of this searching the 10 element. It is for 10 element, and for 30 take. 30 level is what? 2 and probability is 0.1. And plus 40 is what? 3. 40 is 3. Level is 3. And probability is 0.2. Plus. Now these are what? Successful search. I told you cost of the tree always is what? Collection or the sum of successful search and unsuccessful search. Even you have to calculate unsuccessful search. So in unsuccessful search, the first is what? It is 0.1. So you have to even write the level as you wrote for the other nodes. You have to write for square nodes. Square nodes first element is this, and the level you can find it is in 3, but actually it is in 2, because as element is not there, you cannot come to down, right? So you will take again 2. 2 into 0.1 plus 2 into 0.5 plus unsuccessful 2 into 0.1 plus 2 into 0.5 plus 2 into 0.15 plus 3 into 0.5 plus 3 into 0.5, right? Now, so here I wrote here 3. 3 is what? Level minus 1. It seems to be level 4. That's what we were taken, level minus 1, which is 3. So finally, if you calculate, you will get 2.1. Successful nodes, that is started with 1 into 0.2 plus 2 into 0.1 plus 2 into 0.1 plus 3 into 0.2 plus unsuccessful node. So finally, it is what? Cost of a binary search tree, considering successful search and unsuccessful search. The formula is what? How the way I have calculated? Cost 0 comma 4, that means 0 comma n, is equal to probability, that is pi into, it is pi into level of ai, the nodes level. So it is not for single element. I wrote here I. So I value lies from 1 to n plus. How I calculated this cost? Probability of this plus qi into level ei minus 1. Right? Now, for it, I represented it is I. I starts from where? 0 less than I less than or equal to n. So this is what cost of this tree, to calculate cost of a tree. That means cost of a node is calculated with the probability and level. Cost of a tree is calculated with the probability into level plus it is what successful and it is what unsuccessful. Put together, you will get the cost of the particular binary search tree. Now, what is optimal binary search tree? Optimal binary search tree is, it is a problem to be solved, and the problem is what? That if the key is given and the probabilities pi, qi is given, we have to generate a binary search tree such that the cost is minimum. This is what optimal binary search tree. Now, so how I can apply dynamic programming on this optimal binary search tree, and what is the procedure to approach dynamic programming? We'll take an example in the next video and we'll be going to find the solution by applying dynamic programming. Thank you all.